Okay, a couple things I guess this is from yesterday. Just quick reminder, when we're solving rational equations, remember we're just finding the least common denominator. And, here denominator is 1, right? Finding the least common denominator and distributing that through both sides to clear all the fractions, just like we would do with numbers. And then we solve a simple equation once we get rid of all the fractions, right? But we have to remember that before we do that, we have to make a list of all the values of x that have to be excluded from the domain. So any solutions that coincide with a value that has to be excluded don't count, right? So in this case, we didn't get that. All right, so in this case, that didn't happen. But in this case, did it? Let's see. One of them it did, didn't it? Yeah, in this case it did, right? So in this case, we found the least common denominator. We multiplied both sides through by that. We got a much easier equation. When we solved the quadratic equation, we got two solutions. But one of those two solutions was a value that had to be excluded, right? So we had to cancel that one out, okay? All right, so this is where we left off then. We just have about 10 left to do, 10 or 11 left to do. So we're just solving, and this is, it's not hard stuff, right? The majority of this of the placement test is quadratic equation stuff, right? So it's really stuff we've been doing for a long time. It's not hard, but you gotta be careful with it, right? You only get one retake on this. Yes, sir?
I had it said 24.
You had what?
I said 24, and we weren't done with it yet.
Yeah.
Was it not this one?
No.
Okay. Let's see. Okay, what about this?
Dang it, I just write out.
Back to it. Sorry about that. What about this? What are we doing? So what's our strategy for a problem like this? Isolate x. So what are the steps to isolate x? Subtract 18, then divide by 3, then square root. Yeah. Okay, so if we do that stuff, if we subtract 18, we get 3x squared equals what, 30? Divide by 3, we get x squared equals 10. So what's that?
Plus or minus.
Plus or minus root 10. And we just want to separate them with a comma. So root 10, comma, negative root 10, right? Okay? Okay, what about this one? Square root. Okay, good. Once again, we're just going to isolate x. We can point to a single x. It's quadratic, and we can point to a single x. So all we have to do is isolate that x. So we square root both sides. What's that give us?
4x minus 3.
Plus or minus. Good. Plus or minus 5. Now what?
3.
Where's the 3 go?
In front.
Okay, we want to put in front of the plus or minus. Okay, because now we can already see we're going to divide both sides by 4. Because these are numbers that combine easily, no square roots, no i's, we could just have one common denominator. Divide each side by 4. And so if we take the plus, we get x equals 3 plus 5 is 8 over 4. What's that? 2. If we take the minus, we get negative 2 over 4. So those are my two solutions. Okay? All right, what about this? So discriminant stuff, right? So there's some pull downs on this question. That based on the value of the discriminant, you're going to choose two things based on the value of the discriminant. It's either negative, positive, or zero value, which is going to tell you that one of these three options has to be true, right? So quick reminder, if if we've got a quadratic equation in standard form, and here's the important thing, it's gotta equal 0, right? Can't forget that part, equals 0. And we know that the quadratic formula follows, so x is negative b
Plus or minus radical square root b squared. Minus square root divided by 2a.
Okay, well, the part that we're interested in here is
So radical. That's right.
that part, right? That's the discriminant. Right? It's the part that sits under the radical in the quadratic formula. That's the crucial part because that's the part that determines if we get i's or not. Right? We get i's if we have a negative number under the radical. So we know that if the discriminant is less than 0, then what's that tell us? We get a negative discriminant. What do we know we're going to get? Yeah, good. We're going to get 2 imaginary solutions. If the discriminant is positive, what's that tell us? How many are we going to get? 2, right? 1 for the plus and 1 for the minus, right? In our plus or minus. 2 real solutions. And then in the in-between case, if it happens to be exactly equal to 0, what's that tell us?
1
Yeah, we get 1, real or imaginary?
real. Unless it's negative 0.
And it's 1 real, but now that we've gone a little further ahead, we know it's 1 real, but we also know that this 1 real has a multiplicity of what? Because if it's a quadratic equation, you know, we're finding the zeros of a quadratic polynomial, we know we have 2 complex zeros. So it only shows up as 1, but it counts as 2,
Yep.
right? I mean, it really is one individual solution, but it has a multiplicity of 2. Okay, but up here, that would mean that result, right? So what do we get here? If we do this one, what do I have to do first?
Put it in standard form.
You gotta put it in standard form, so I'm gonna add 2x to both sides. So I'm gonna get 2x squared minus 2x, I'm gonna add 1 plus 3 equals 0. Okay, so then we just need to know what's the value of b squared minus 4ac. So that's gonna give us 4 minus, negative 2 squared, right? 4 minus 4 times 2 times 3, well, clearly that's negative, isn't it? Right? So if it's negative, that means, yeah, we're getting 2 complex solutions with i's, right? Okay? All right, so on to this, simplify the expression. Okay, so this is where we kind of different order, this is where we left off yesterday. So we could do this with fractional exponents. Let me just show you that way. But then there's maybe a shortcut here because we're talking about square roots. Yeah. I am recording. Thanks for checking. So we could write this then. Let's first of all, is there anything we can do inside to simplify things? Well, no. 45 over 7 doesn't simplify. I don't have any like bases, so I'm kind of stuck with things the way they are. But at the very least, I can rewrite this. I can separate the top and the bottom, right? So I can write this. There we go. So I can write this as the square root
45
of 45x to the 5th divided by the square root of 7y, right? Okay, and then we can use our trick on the top and the bottom there, right? Where if we want to simplify this, there's nothing comes out on the bottom, but on the top, some stuff does come out, right? I can break the top into some outside stuff and some inside stuff. What about the number 45? What comes out? 3, okay. I get a square root of 9, and inside I get 5, good. And then I have a square root of x to the 5th. Well, that's the same as x to the 5 halves. So what comes out and what stays in?
2x squared.
X squared goes out, and x to the 1, and I'm going to make that 1 really light because we don't write it, but it's there, right? So outside I get x to the 2, inside I get x to the 1 half, right? And once again, we wouldn't write those numbers, but they're there. On the bottom, we're stuck with the square root of 7y. Nothing comes out. Okay, so now what do we do? The top is done, but the bottom is not. What's wrong with the bottom?
Tens in the
We got
basement.
tens in the basement. We can't do that. Right, so let's do the easy way first. So because we've got square roots, what do we always say if we've got a stranded radical in the denominator? What do we always do? Multiply top and bottom by that, right, by that stranded radical. So we can multiply both the top and the bottom by the square root of 7y.
How come you wouldn't multiply by radical versus simplify the top first?
Okay, so we want to take that? How come we wouldn't multiply by the radical first?
So we can get things.
Well, the question is, why do we simplify the top first before we multiply top and bottom by the square root of 7y? It would work both ways, but this is better. What do you think? Makes it easier, yeah. Then we get a much smaller number to deal with in here, right? We'd rather deal with simplifying small, especially the number part. Right? We want to simplify the square root of 45 instead of the square root of 45 times 7, that's 315. I don't want to do that. Square root of 315 is hard to simplify.
Oh,
Right?
it's gonna be 3x squared.
So then, okay, so then on the bottom, if I multiply a square root times itself, it cancels the square root, right? So we end up with what we want on the bottom, which is a 7y. On the top, I've got three things being multiplied. I've got 3x squared times the square root of 5x times the square root of 7y. Well, let's multiply these two first, right, obviously. Those are the two we want to multiply together to make one radical. So we've got this times this times this. We'll multiply those together, and we end up with 3x squared. And then all this stuff, a square root of a times a square root of b is a square root of a times b, right? That's a property we have. That makes sense, right? I can combine radicals by multiplying. So then inside, we're just going to get square root of 5 times 7 is 35 xy. And 35 I can't do anything with, right? Okay. So that's our answer. You know, I won't even, we'll just talk through this real quick. So what else could we have done? What if this was a cube root instead of a square root? And that's not going to show up on the final, but just for future reference. What if that was a cube root? If that was a cube root, we couldn't just multiply. What if we had the same thing? But let's make this cube root of 5x on the top and cube root of 7y on the bottom. What if? I can't just multiply by the cube root of 7y this time, can I? Right? Because then I'm going to get the cube root of 49y squared, and that's I still got a 10 in the basement. Right? So what we do here instead is we would take this stuff and we'd write them as fractional exponents. So I'd end up with my 3x squared, and I'm going to get a 5 to the 1/3 times an x to the 1/3 divided by 7 to the 1/3 times y to the 1/3. Right? Make sense? Okay, so now we got to get. I've got bases of 7 and y in the denominator. Tenths in the basement, radicals in the denominator correspond to fractional exponents. So I need to do the easiest thing I can to get whole number exponents in the bottom, right? So I would have to multiply top and bottom by 7 to some power. Well, what power of 7 would I need to multiply to get the easiest whole number on the bottom? 2/3, right? Because I'm moving up. 1/3 is between the integers 0 and 1, right? So I want to move up to the next available integer, which is 1. In order to move up to 1 from 1/3, I need to multiply by 2/3 on the bottom.
This will or will not be on the test?
It won't, but I want you to know it anyway.
Oh, it'll be easy if it is.
Okay, so then that's going to give me, if I do that stuff, that's gonna give me, on the bottom, I'm gonna get my 7 to the 1/3 plus 2/3, so there's my 7. I gotta do the same thing for the y, right? I'm gonna multiply by y to the 2/3 over y to the 2/3, which just gives me my y on the bottom. Now on the top, I've got all this stuff out front, and that's still there. Okay, but what about this? Now, notice that all of these denominators are 3's, right? If they weren't, I'd have to write separate radicals on the top, but in this case, I have denominators of 3 and all my fractional exponents, so I could combine those because I've got that. Because I've got 3's in all my denominators, I've just got one big cube root, and what goes in there? Well, I've got a 5 times a 7 squared, right? Let's just do it this way. I've got 5 times x, and those are both to the 1, times 7 squared times y squared. Right? So then, what's that work out to be? Well, 7 squared is 49, times 5 is what, 245?
Yeah.
So I get 3x squared times the cube root of 245, x to the 1, y squared, divided by 7y. Okay? Makes sense? Now, do I have to worry about this 245? Are there any perfect cubes in 245? We can tell immediately if there are or aren't.
Probably not.
There aren't, because how did we get 245?
Multiply by random numbers.
5 times 7 times 7, right? So the only factors we used were 5 and 7 are both prime. So there's no way I could have any perfect cubes that are factors of 245 if it's a product of the prime number 5 and the prime number 7 squared, right? And we could try, but we're not going to find it. That make sense? That's a little bit more advanced. I mean, I think I probably gave you a couple like that on the homeworks that are similar to that, but nothing like that will show up on the final. On the final, it's only going to be square roots. Square roots, it's easy. We don't have to turn them into fractional exponents. If we get a stranded square root on the bottom, we just multiply top and bottom by that square root to clear it, right? The rationalized denominator. Questions? Okay? Very, very simple. What do I do here?
Distribute.
Distribute. So if I distribute the radical x, square root of x times square root of x is x minus 2 square root of x. If I distribute the 5, I'm going to get a plus 5 radical x minus 10. And if I add all that stuff up, I get x plus 3 radical x minus 10. No big deal, right? No big deal. Okay? Okay, and finally we're on to some of the most recent stuff we've been doing. Not hard. None of this is really very hard. The average test score on this test is like the highest by far of any we've taken. It's the easiest stuff I think we've probably done. What do I do here?
Square root.
No, square root both sides. Square both sides. So if I square both sides, if I square both sides, what do I get?
X plus 10 plus 21
Equals 121. Okay, so if I subtract 21,
That's a cool number.
equals 100. So do I know it's right?
No.
Gotta go back to the step before I squared anything, right? Before I took both sides to a power. So I plug it up there. I can try it. Does it work?
Yes.
It does. So that's my solution.
Still don't understand. We did it.
Okay, what about this one? Hey, listen, please don't, I want to get through this efficiently. I'm here, don't talk right now. I mean, if there's, just hold off on that. You have plenty of time. What do we do here? Square both sides. I can square both sides. If I do, I eliminate both the radicals. You could also think of this, that's fine to do. We talked about the strategy is isolate the radicals and square both sides, but you can also see another pattern here. If I've got the square root of A equals the square root of B, then just by symmetry, whatever's inside this radical I do that like every time. So whatever's inside that radical has to equal whatever's inside that radical. If I've got a square root of something on the left, if there's a square root of something on the right,
Plug in and right.
don't they have to be equal? Right. So we, even without squaring both sides, we get the same equation. So I would just set these by either squaring or not, I'm gonna get negative 5x plus 6 equals negative 10x plus 10. Let's add the 10x to this side, so I get a 5x. Let's subtract the 6 from this side, so I get a 4. I divide by 5. So 4/5 is my answer. I gotta check it. If I plug that back up here, negative 5 times 4/5 is what?
-4.
Negative 4. Negative 4 plus 6 is positive 2, so that would give me square root of 2 equals, how about over here? 4/5 times negative 10 is negative 8 plus 10. So it works. Right, that's a solution. Okay. How about this one? Square both sides.
Oh, got him. You did it.
So we cancel the radical, we get a negative 4x minus 11 equals what? Plus 8x plus 16. Now what? Get it all on one side. So we'll add 4x to both sides. I'll add 11. And the whole thing's equal to 0, right? Okay, now what? Magic numbers, good. What do we get?
-9. -3. Do we know?
Okay, we good?
No.
No, we're not. Good.
Plug it in.
Look into the recipe squares.
Okay, plug them in, right? If I try them both, what happens? The original square root equation, right? So if I try the negative 3,
It's gonna be an I.
No, it's not, it's fine.
Okay, it's not. Fine.
so if I try negative 3, I'm gonna get the square root of negative 4 times negative 3 is 12.
Yeah.
Minus 11, so the square root of 1, does that equal the square root of negative, or does that equal negative 3 plus 4?
Yeah.
Yes.
It does. So negative 3 gets checked. Okay, what about if we try x equals negative 9?
It won't work.
No,
I'm gonna get the square root of 36 minus 11, that's the square root of 25. Is that equal to negative 5?
no.
Okay, so we have to eliminate that one. We can only keep the negative 3. Okay? What about this? Square both sides. Okay, what do I get on the left side? Now you gotta be careful with this. This is just the a plus b squared pattern, right?
X plus 3.
Okay, so I'm gonna get a squared, that undoes the radicals, so I get an x plus 3
Plus.
plus 2 times a times b, so
Oh,
that's
yeah.
4 times square root of x plus 3, right? Plus b squared is 4. Does that make sense for the left side? Just following my expansion pattern for a plus b squared. And then on this side, it just eliminates the radical. I get x plus 19. So now what?
Combine like term.
Combine like terms. So on this side, I'm gonna get x, and I get a 3 plus 4, so I get x plus 7 plus 4 times the square root of x plus 3 equals x plus 19. Now what?
Where did the
Subtract X.
Okay, because I'm just, what do I do if I've got
A squared plus B squared.
a plus b
Squared.
squared? What's my pattern?
A plus
A
squared plus BB. Would be
2ab.
plus, sorry.
There you go. So a is x plus 3, square root of x plus 3, and b is 2. Okay? All right, so now what are we doing here?
Oh, subtract the x.
And why? What am I trying to do?
Isolate the radical.
Got to isolate the radical. Remember, the rules are, if we're solving a radical equation, we've got to isolate a radical to get rid of it. So I'm going to isolate the radical on the right side and square both sides to undo that radical. But then I've got another one in here that I've got to isolate also algebraically and then square both sides to undo it, right? So we'll subtract x from both sides, cancel the x's. I'm going to subtract 7, and I get 4 times the square root of x plus 3 equals 12. Now what? Divide by 4. Last step,
Square both sides.
square both sides.
Definitely not.
Last step.
X equals 0?
Okay, so last step,
Subtract 3.
we good?
No.
Maybe, you gotta check. So we go back and we check 6 in the original problem. If we do that, we're gonna get the square root of 6 plus 3.
9.
So that gives us a 3. How about on this side?
25. 5.
Okay, so that works, doesn't it?
It does.
Okay, so we get
6 plus 19 is 25.
checks out. So that's our one solution. All right. Okay, very last two things, extremely simple, adding and multiplying complex numbers. Adding complex numbers couldn't be easier. What do you do?
Combine like terms.
Combine like terms. So I'm gonna combine the constants and the I terms. So that's gonna give, didn't we do this one yesterday?
No.
Okay. So we get negative 10 if I combine the negative 15
And 0.
and the 5, and I get 0 if I combine the 3i and the minus 3i. So there is no I term in this case. That's it.
Wow.
Okay? All right, last one.
Multiply.
So we're gonna just expand it out, and remember, we just treat the I like a variable. In that last example, we just treat the I like an x and we add like terms. Same thing here, but there's one little part we have to remember. So if I distribute the 6, I'm gonna get, 78 minus 54i. If I distribute the 6i, I'm gonna get, what is that? 78i.
Plus 54.
Okay, minus 54 I squared. But what is I squared equal to? Negative 1. Good. Remember that I squared is negative 1. So when we multiply out complex numbers, we always know that whenever we get that I squared, it's just going to change the sign of that term, isn't it? Right? So we end up then with 78 minus 54i plus 78i, and then that just becomes a plus 54. Now I just combine like terms. So 78 plus 54 is 132, and then if I combine negative 54i plus 78i, what is that, 24i? Okay, make sense?